So far we have talked about a system having energy, and we said, if you recall, that in the reaction of hydrogen and chlorine, there was a transfer of energy from the kinetic energy and potential energy from reactants to potential kinetic energy and potential energy of products. We said that energy was constant in the system. There was just an exchange of different forms of energy. The products were moving faster because there was more kinetic energy and there was less potential energy. All right. And we said energy was constant. What we're going to do now is what happens when this system, or when any system exchanges energy, when your system may lose energy to the surroundings, or when the surroundings provide energy into the system. And we may be a little bit new with this, but this nomenclature means that when the increment of energy is negative, and the increment is defined always as final minus initial, if your final is lower than the initial, this will be negative, your system loses energy, okay? And when this increment down here, for example, is positive, it means that your final is higher than the initial. This is positive. If this is positive, your system gains energy from the surroundings, okay? So this form that we said, of course, could be explained in terms of atomic level. Where did the system got energy? Well, maybe the surroundings provided kinetic or potential energy. But the most common formulation of this principle is in the macroscopic form, and this, ladies and gentlemen, is the first law of thermodynamics, in which it says that the change of energy of a system can be positive or negative, and it can be because of either heat or work. So if a system changes its internal energy, it'll be because it has gained or lost heat or gained or lost work. So there's also special nomenclature, and let me give you an example with it. As we said, when the increment of energy is negative, it means that it loses energy to the surroundings. We call this process exothermic. And in this case, imagine such as a biker who's running his bike for an hour. It loses a lot of energy, both in form of heat and in form of work, if you will. It will lose energy. That's exothermic. When the increment of energy of the system is positive, it means that the system gains energy. We call this process endothermic. So think of I don't know if you have ever seen this, neither have I, but it's typical in movies, right? A clown in a canoe, so the clown is your system, the canoe and the surroundings provide a lot of, in this case, kinetic energy. So the final energy of the clown is much higher, both in heat and in work, okay? So, in this slide, there is a little bit of theory. You may spend some time reading through this. Thermodynamics, by definition, will have a fair amount of theory. It's important that you spend some time reading through it, but we will not use video time for explaining that. So I think it's better if we solve a problem so that what we just said, that the first law of thermodynamics is the change of energy of a system has to be because of the work or the heat being exchanged with the system. Let's give an example, because this is fairly abstract. So in this case, it says there is a red hot piece of lead dropped into water. Okay, so let's imagine that this is water, and we throw some hot piece of lead. First of all, if it's red hot, it means that the temperature of lead has to be higher than the temperature of water, because water, if it's water liquid, cannot be higher than 100 Celsius, and lead is not red hot at 100 Celsius. Okay, so we throw the red hot piece of lead, and it's asking if is the process exothermic or endothermic. Well, what you can imagine is that if you throw a red hot piece of lead in water, there will be some heat going from lead to the water. Okay, when the heat is lost, when heat or work is lost, the sign of heat and work is negative. Okay, negative. Okay, when the heat or work is gained, the sign will be positive. So in this case, because it's lost, there is no work involved. So this means that this is Q, the heat of the system. This Q is negative. Therefore, this is negative. This is an exothermic process. It makes sense. This is just a convention, but so that if for the heat to be negative, it means that the whole change of energy is of lead of your system is negative. Therefore, lead is losing energy. Okay, in form of heat in this case. All right. So let's see if any of these sentences are true or false. So let's say it says that the increment of temperature of lead is negative. Well, we know that the increment of temperature of lead is final minus initial. So what is higher? The lower, the final temperature or the initial temperature? At the beginning it was red hot. Finally it will reach a thermal equilibrium with water. So it means that this one is lower than, and the initial was higher. Therefore, you are subtracting a larger number. This will be negative. So this is correct. Okay. Now, it says that the heat that lead loses is equal to the heat of water. And this may be, in terms of the conservation of energy, this should make sense. However, notice that there should be a change of sign. So what is really true is that the negative heat of lead is equal to the positive heat of water. In other words, let's put some numbers into it. If this red hot piece of lead were to lose 10 joules, which would be a very tiny piece of lead, if the heat of lead would be negative 10 joules, and for conservation of energy, and there is no work, the heat of water would be positive 10 joules. That's a little bit what I'm trying to say here. They're only equal if you change the sign of one of them. So this is not exactly correct. Okay, there's a change of sign involved. And this is just a question that we already answered. The heat of water is positive. Yes, it is, because water gains energy. And as we set up here, when the heat or work is lost, the sign is negative. When the heat of work is gained, the sign is positive. Water gains energy in the form of heat. Therefore, water is positive. Okay. The final temperature, it says that water, and this should be lead. Okay, so I don't know why it's iron. Well, does it make sense? We will talk about that. But just so you know that the question never says how much lead we are throwing. So imagine that you have a big container of water and you're throwing a little bit of lead. Of course, the final temperature will be different than if in the whole container of water you're throwing a big rock of lead, right? Can you imagine? The final temperature will be different. Therefore, this formula does not take into account the mass of lead or water that we're throwing in. We will talk about it, about this kind of problems, but just using this intuition, we can already say that this is false, because this formula does not include any mass of water, neither water nor lead.